So real briefly, we're going to look at a couple more things before getting to our first device. So the first thing I want to look at is our Einstein relation. And so what this does is it relates our diffusion coefficient and our carrier mobility. So we're sort of relating between our diffusion current and our drift current. And so what this relation is it says that our dN divided by mu n, so our diffusion coefficient divided by our electron mobility, is equal to our diffusion coefficient for our holes divided by our mobility for our holes, mu sub p, and both of those are equal to kT over Q, where this K is our Boltzmann constant, T is our temperature, and Q is the magnitude of charge over the electron. And so we use this quantity a lot in semiconductor physics and in microelectronics, so much so that we're going to call it V sub T, and we're going to say that this is something called our thermal voltage. And so it's worth noting that at room temperature, so if we're talking about roughly 300 Kelvin, we have that our Vt, which is again equal to kT over Q, is approximately 0.026 volts, which is of course 26 millivolts. And so that's an important value to know that might save you some steps on some fundamentals of engineering exam problems, or it just might be useful in other circumstances as well. So that's our Einstein relationship and our thermal voltage. One other thing I want to write out explicitly is that, of course, our overall current density in the material, let's call it J total in some semiconductor, is going to be equal to the contributions from our drift current density as well as our diffusion current density. And so as we've seen, of course, we can break each of these two down further. So we could say that our J total is equal to our J drift, which is composed of J drift due to electrons plus J drift due to holes, plus our diffusion term, which is J diffusion due to electrons plus J diffusion due to holes. And as we saw explicitly in the example where we were just looking at drift, typically one of these is going to dominate. So typically one term dominates, but that's at a given time in a given region of the semiconductor. And so talking about certain times and certain regions, hopefully that will all make sense here in a little bit when we start talking about devices. And so what that means is if we know sort of what we're doing and we can sort of accurately predict, we don't need to calculate each of these four, but we could say, well, maybe this one right here is dominating, so we just have to calculate that for this time in this region, and that's going to give us a good approximation.